if you are given questions on calculation in electrolysis, how do you attempt it? Now, you need to understand some principles behind the reactions of electrolysis, and I've made a video on that. You can always check that. But for this question, now we have to calculate current that will deposit 3.25 grams of zinc in 2 hours. Zinc, which is electropositive, will go to it's part of the ions that will go to the cathode, and the cathode, which is negative electrode, and they go there to undergo reduction, which is gain of electron. So writing this equation of reaction, it is very important for you to know the charges that each element carries. That is the form of their ions. For instance, now zinc carries +2 charge, so it picks up 2 electrons to produce or to deposit zinc metal, which is just 1 mole. So in this case now, we should also know that 1 mole of electron is equivalent to 1 Faraday. 1 mole of electron is equivalent to 1 Faraday, which is also equivalent to 96,500 coulombs. Now, there is a formula that we can use here, and that is Q, which is quantity of electricity, and it is in coulombs. Say, is equal to the product of current, which is in ampere. That's I in current, and T is time. The time must be in seconds. If the time is given in hour, you need to multiply by 60 twice. If it is given in minutes, you need to multiply by 60 once. And if it's in second, you use it directly. So time here is in seconds. Now, we have to calculate current, and current is here. We know the time as 2 hours. We need to calculate current, but we don't know the quantity of electricity because nothing like that was given in the question. Only 3.25 grams, which is mass of zinc, was given. So we go back to this equation. When we get the first line from this equation, which is 2 moles of electron, which is 2 Faradays, liberate 1 mole of zinc. And 1 mole of zinc, we need to convert it to mass because we are talking about mass of zinc in this case. Then 1 mole of an element is its atomic mass or mass number. And zinc has atomic weight or atomic mass of 65.3. So 2 Faradays yield 65.3 grams of zinc. But in this question, Q is not in Faraday but in coulombs. So 2 Faradays will be 2 multiplied by 96,500 coulombs. Since 1 Faraday is equivalent to 96,500 coulombs, 2 Faraday will be 2 multiplied by 96,500 coulombs, which produces 65.3 grams. So the question now is 3.25 grams will be produced by what coulomb of electricity? In this case now, we need to work out the coulombs by dividing, we multiply this by 3.25, then divide both sides by 65.3. So in this case, we get the quantity of electricity, which is in coulombs, as Q. We will end up getting it as 9,590 coulombs. Now from here, we can now go back to this formula, which is Q equals to IT. Now, Q has been given as 9,590 coulombs. The current is what we are trying to calculate, and time is 2 hours, which we have to multiply by 60 to convert to minutes, and then multiply by 60 to convert to seconds. So in this case now, 9,590 coulombs equals to current multiplied by 7200 seconds. So dividing both sides by 7200 seconds, current is therefore 1.33 amperes. So 1.33 amperes is the quantity of electricity or current, is a quantity of current that will deposit 3.25 grams of zinc. Assuming you are given a question on calculating the quantity of electricity required to liberate a certain mass of copper, how do we attempt this question? Now, we are to calculate quantity of electricity. It is represented as Q, and the unit is coulombs. So Q equals to current multiplied by time, which must be in seconds. Now, let's look at the question. Is anything like current and time in the question? No. But we were asked to calculate quantity of electricity required to liberate 10 grams of copper. And in electrolysis, it requires a certain amount of, or a certain quantity of electricity for an element to be discharged. So in this case now, we can still write the half reaction since it's involving copper. Copper carries +2. It goes to the cathode because it's a positive ion going to the negative electrode, which is the cathode, to pick up electron. That is reduction, while oxidation occurs at the anode to give copper solid. And the equation is balanced. So it requires 2 moles of electron, 2 moles of electrons to liberate or to produce 1 mole of copper from this half reaction. And 1 mole of electron is equivalent to 96,500 coulombs. So 2 moles of electron is 2 multiplied by 96,500 coulombs, because that is 2 Faradays. 1 Faraday is 96,500 coulombs. So we have 2 Faradays here producing 1 mole of copper. Now 2 Faraday is in 96,500 multiplied by 2 coulombs, because we were asked to calculate the quantity of electricity, which must be in coulombs. And looking at the options here, the answers are in coulombs. So we have to convert Faradays to coulombs. But if the question is to calculate the number of Faradays, we have to just leave the answer in form of Faraday instead of converting to coulombs. Now, it discharges 1 mole of copper. Now, from the question, we are talking about mass, which is in gram. Now, so from this half reaction, we get this first line, 2 Faraday equals to, that's from these 2 electrons, equals to 1 mole of copper. 1 mole of an element is known to be its atomic mass or molar mass. So 1 mole of copper in gram is 64. 64 gram is the molar mass of copper. So what quantity, which is x coulombs, will liberate 10 gram from the question? We can say gram is under gram, quantity of electricity is under quantity of electricity. So x multiplied by 64 equals to 10 multiplied by 2 multiplied by 96,500 coulombs. Dividing both sides by 64, our answer gives 30,156 coulombs as our answer, which is in option A. Now, let's consider this question. You were given a question involving 2 elements, zinc and mercury, in the calculation of electrolysis. And we are to determine the mass that will be of one of the elements that will be discharged using the same quantity of electricity. This is based on the second law of Faraday. Now, what to do here? We need to write the half reaction. If a given quantity of electricity liberated 0.65 gram of zinc, 2 ion, what amount of mercury, 2 ion, would be liberated by the same quantity of electricity? Now we're given some information here. Zinc atomic mass or mass number is 65 gram, while mercury is 201 gram. So now the first thing is to determine the quantity, that same quantity that discharged 0.65 gram, that was not given. If a given quantity, it was not given to us, so we need to work it out first. They now ask us that what amount of mercury, that's another, bringing another element in now, would be liberated by the same quantity of electricity. So, the same quantity of electricity, so we need to calculate the quantity of electricity first. That requires 0.65 gram of zinc to be discharged. So, writing the half reaction, zinc is electropositive. It goes to the negative cathode to pick up 2 electrons that it has lost before when it became an ion. It picks it up to become neutral zinc. That is zinc's solid. So here now, reduction is taking place. It means that 2 Faradays is required to produce 1 mole of zinc from this equation, because zinc carries +2. And 2 Faraday is equivalent to 2 moles of electron is equivalent to 2 Faraday, which is also equivalent to 2 multiplied by 96,500 coulombs. Since 1 Faraday is equivalent to 1 mole of electron, which is also 96,500 coulombs. So 2 multiplied by 96,500 produces 1 mole of zinc. Now, if you look at the question, they are not talking about mole. They are talking about mass, which is 0.65 gram of zinc. So here now we have 2 multiplied by 96,500 coulombs requiring or producing 1 mole of zinc. 1 mole of zinc is its atomic mass. 1 mole of an element is equal to its atomic mass or mass number. You can see this first line we are getting is from the half reaction. That is the trick behind it. You get one from the half reaction, you get the second line from the question, and you cross multiply and get your answer. So these 2 Faradays liberate 1 mole of zinc, which is equivalent to, what's the information there? Zinc is 65 grams. That's the atomic mass. Since 1 mole of an element is its atomic mass. Now, what quantity here, which is in coulombs? X coulomb, I love using S to represent the unknown, will be required to discharge 0.65 gram. So that is what we want to find out. X multiplied by 65 gram equals to 2 multiplied by 96,500 coulombs multiplied by 0.65. So dividing both sides, we have 1,930 coulombs is what we have. So from here now, it means that it requires 1,930 coulombs to also liberate mercury, because they are asking us that what amount of mercury would be liberated by the same quantity of current that discharge 0.65 gram of zinc. So 1,930 coulombs of electricity liberate or produces 0.65 gram of zinc. We will now use the same quantity to calculate what mass of zinc will be produced. Now, if we had of mercury rather. Now, for mercury is also positive. It picks up 2 electrons as well, because from the question we can see it's divalent, and it yields 1 mole of silver. So 2 Faradays here, which is equivalent to 2 multiplied by 96,500 coulombs, liberate 1 mole of mercury. And 1 mole of mercury is its atomic mass, which is equivalent to 201 as given in the question. So let's rewrite this. 2 multiplied by 96,500 coulombs is required to produce 201 gram of mercury. Now, this is from the half reaction. Now, what mass will be produced by 1,930 that did the same to zinc? So 1,930 from zinc, that was required to liberate 0.65 gram of zinc. If it is now used for mercury, what mass will be discharged? That is the question. That is X gram. You can see here now, that is in the second Faraday's law of electrolysis, which says that when the same quantity of electricity is passing through different electrolytes, that statement alone, as this question has justified that statement, that it's possible for the same quantity of electricity to pass through different electrolytes, which contains different elements. So different masses of such elements will be discharged. So 2 multiplied by 96,500 coulombs multiplied by X equals to 1,930 multiplied by 201. So dividing both sides by 96,500 multiplied by 2, our answer yields X is 2.01 gram. And if you look at the option here, that is option B. Now, let's consider this question. Jamb 2024, number 15. A solution P of a mercury salt is electrolyzed. If a current of 5.36 ampere is passed through P for 2 hours, generating 40.2 gram of mercury, P is likely to be what? Now, all the questions that we have come across most times in calculation of electrolysis has been to calculate either time, mass, quantity of electricity, and so on. But in this case now, we are to determine what kind of solution is mercury used for. We know that mercury, we may even be asked to calculate the number of moles of mercury or the charges that mercury carries. But in this case, now we asked to calculate, to get or deduce the kind of solution. Is it mercury iodide or mercury trioxynitrate 5 or mercury tetrasulfate 6 or mercury trioxosulfate 4? Which of these options are correct? Now, the best thing is to work out this using Q equals to IT. The current here is 5.36. The time is 2 hours. Let's work out the quantity of electricity first from this information. So using Q equals to 5.36 multiplied by time, 2 hours, but the time must always be in seconds. That is 60 multiplied by 60 multiplied by 2. That's 2 hours converted to seconds, or 2 hours to minutes first, that's multiplied by 60, and then to seconds multiplied by 60. So that's 5.36 multiplied by 7,200. Now that gives us 38,592 coulombs. Now the next thing is, it means that the next thing is to get the quantity of electricity that we actually liberate 1 mole of mercury. How? They said, according to this information, 5.36 ampere and 2 hours, which we use to generate quantity, liberate or produce 40.2 grams of mercury. That is the question. So it means that 38,592 coulombs produces 40.2 grams mercury from the question. What is P? Now, how do we get or deduce P? Now, most times when I'm treating calculation in electrolysis, I usually write the half reaction. But in this case, we don't know what mercury carries, whether, for instance, now, looking at this solution, this 2 is from mercury. You know, in the formation of compounds, the radicals, the charges that element carries, they exchange their valences, radicals exchange their valences. So in this case now, we can see here that this must have been 4. By the time, because if this is 2, then we cancel out. It can never give us this. If this is 4, the 2 we cancel this, so we have the remaining 2 coming here. So mercury should be 4 here, and in this case, it means that this 3 here is coming from mercury, while SO4 carries -2, exchanging their radicals. That's why we have this 2 here coming down here, and this 3 here coming here. So in this case, now mercury carries +3 as the charge. Now, in the second option here, this 2 is coming from mercury, because mercury here, if it is 2, and trioxynitrate carries -1. Exchanging the valency gives us this information. So mercury is 2 here, and in this case too, if mercury carries +2, iodine is actually -1. So if they are writing 1 here, there's nothing like this, because iodine is always -1. So this information, this first option does not even exist. So, and they want to know what kind of solution is P. We know there is a mercury salt, but what kind of solution is it? So the best thing is to get the exact charges that mercury carries. From there, we can get the kind of solution it is. Now, and we know that we can get charges when we write, okay, the half reaction. For instance, if I give you 2+ here, I will say, okay, mercury picks up 2 electrons to liberate 1 mole of mercury. But in this case, we don't, and these 2 electrons liberate 1 mole of mercury, meaning 2 Faradays, which is also 2 multiplied by 96,500 coulombs, liberates 1 mole of mercury. But we don't know the charges that mercury carries, so we can't even determine the Faraday or the quantity of electricity. But we know that X coulomb here, that is unknown, that we are trying to get, if we get the number of mole, if we get the number of electrons that is required by getting the charges that mercury carries, for instance, like this now, this is unknown, so we can't determine what is here, which is also X, but we know that it will yield mercury. So 1 mole of mercury, so to say, and or it can be 2 or 3. This will determine the charges that we have here, which is positive, will determine what is here, and will also determine the number of mole here. Since we don't know that, this here is electron, and it determines the Faraday or quantity. So if we don't know it, we won't know the charges, and we won't know the solution. Now, so here now, Xa liberates 1 mole of mercury, 1 mole of mercury, and 1 mole of mercury, 1 mole of any element is its atomic mass. So 1 mole of mercury definitely is, what's the atomic mass of mercury in the information given to us? Mercury, 1 mole of mercury in the information given to us is 201. So 201 gram. So I'm going to clean this and replace it with 201. We don't know the number of Faraday or number of electrons that is required to liberate 201, which is the atomic mass of mercury, because 1 mole of any element is its atomic mass. So if we are able to work out this, we will know the kind of element. So X multiplied by 40.2 equals to 201 multiplied by 38,592 coulombs. Dividing both sides by 40.2, X gives us 192,960 coulombs by calculating this. So this is the quantity of electricity that will liberate 1 mole of mercury, which is its atomic mass, and that is 201 gram. So we need to know the number of electrons, which also determines the charges that mercury carries from this quantity of electricity. What's the relationship? 1 mole of electron equals to +1 from the charges that an element carries. Like maybe you have mercury as +1. So 2 moles will be 2 plus 2. And 1 mole of electron is equal to 1 Faraday. And 1 Faraday is equal to 96,500 coulombs. So how many Faraday will be in 192,960 coulombs? If you are able to get the number of Faraday, we will get the number of charges or the number of electrons, which is also equivalent to the number of charges. So that's what we are going to do now. So if 192,960 coulombs is liberating X Faraday, 96,500 coulombs, which is a constant for 1 Faraday, is equivalent to 1 Faraday. You can see Faraday is under Faraday. So from here, we have 192,960 coulombs equals to X times 96,500 coulombs. Dividing both sides by 96,500, X is equivalent to, or X is equal to 1.999, which is roughly 2. It means 2 Faraday, which is 2 electrons. So it means that mercury carries +2. So which of this solution contains the actual mercury that we are talking about? Now, I told you that 3 is coming from this mercury. So the charges on mercury here is 3 because whenever compounds are being formed, the radicals that combine together to form such compound exchange their valency. Like mercury here carries +3, SO4 usually carries -2. They will exchange their valencies, and if they are equal, they will cancel out. So in this case now, 3 is coming from mercury, so that is not the answer. Then for option A, there is nothing like, even if mercury here is +2 coming from this side, iodide ion is usually -1, not -2. So this 2 is definitely not from iodine, so it is not correct, even if mercury is carrying 2, which would have been the correct answer. But because iodide ion carries -1, not 2, which is down here, when they exchange, it means this solution does not even exist. So let's look at this option D as well. This 2 is coming from mercury, Hg, and then SO3 is also a radical that carries -2 naturally. So in this case, they are supposed to cancel out if they are the same to give us HgSO3, which does not look like what we have here. So let's look at option B. This 2 is from mercury. So if you have mercury 2, and then NO3 is a radical that carries -1. Now, if you exchange the valency, this -1 is coming down, 2 is coming to this side. So this is the correct answer, which carries +2, and the radicals attached to it is very correct. So 2 Faradays here represent 2 charges. So this is the solution that we are talking about. Now, from the series of calculation and electrolysis that I've made, we can see there that there's nothing new that we have not touched. So I want to encourage you to watch the full series of the calculations extracted from different years, calculation of mass, calculation of time, calculation of number of moles, Faradays or quantity of electricity and so on and so forth. Everything has been covered. And please feel free to subscribe to my channel on Facebook, on YouTube, that is Olabisi Olawoye, and also follow me on Facebook, Olabisi Olawoye. Share my videos, subscribe, press notification bell so that when I upload new videos, you will see it. And we also have a series of beautiful videos that I've made in chemistry. I wish you all the best. Thank you. Assuming you are given a question on calculating the quantity of electricity required to liberate a certain mass of copper, how do we attempt this question? Now, if we are to calculate quantity of electricity, it is represented as Q, and the unit is coulombs. So Q equals to current multiplied by time, which must be in seconds. Now, let's look at the question. Is anything like current and time in the question? No. But we were asked to calculate quantity of electricity required to liberate 10 grams of copper. And in electrolysis, it requires a certain amount of, or a certain quantity of electricity for an element to be discharged. So in this case now, we can still write the half reaction since it's involving copper. Copper carries +2. It goes to the cathode because it's a positive ion going to the negative electrode, which is the cathode, to pick up electron. That is reduction, while oxidation occurs at the anode to give copper solid. And the equation is balanced. So it requires 2 moles of electron, 2 moles of electrons to liberate or to produce 1 mole of copper from this half reaction. And 1 mole of electron is equivalent to 96,500 coulombs. So 2 moles of electron is 2 multiplied by 96,500 coulombs, because that is 2 Faradays. 1 Faraday is 96,500 coulombs. So we have 2 Faradays here producing 1 mole of copper. Now 2 Faraday is in 96,500 multiplied by 2 coulombs, because we were asked to calculate the quantity of electricity, which must be in coulombs. And looking at the options here, the answers are in coulombs. So we have to convert Faradays to coulombs. But if the question is to calculate the number of Faradays, we have to just leave the answer in form of Faraday instead of converting to coulombs. Now, it discharges 1 mole of copper. Now, from the question, we are talking about mass, which is in gram. Now, so from this half reaction, we get this first line, 2 Faraday equals to, that's from these 2 electrons, equals to 1 mole of copper. 1 mole of an element is known to be its atomic mass or molar mass. So 1 mole of copper in gram is 64. 64 gram is the molar mass of copper. So what quantity, which is x coulombs, will liberate 10 gram from the question? We can say gram is under gram, quantity of electricity is under quantity of electricity. So x multiplied by 64 equals to 10 multiplied by 2 multiplied by 96,500 coulombs. Dividing both sides by 64, our answer gives 30,156 coulombs as our answer, which is in option A. If you are given a question involving calculation of mass deposited by a certain quantity of electricity, the first thing is to consider the element itself. Now, in this question, you have to calculate the mass of magnesium that will be deposited by 8 Faradays of electricity. It is normally known that in electrolysis, a direct current is attached to the electrodes, which electricity passes through them, and then they bring about the movement of ions, and those ions move to the anode and cathode respectively. The positive ion moves to the negative cathode, while the positive ions move to the negative cathode. So in this case now, we have to calculate the mass of magnesium that will be deposited by 8 Faradays of electricity. Now, let's consider the reaction here. Magnesium has atomic number of 12. To determine the charges that it carries, we quickly look at the valence electron. Since it's 12, the first shell takes 2, the second shell takes 8, the third shell takes 2. So we have +2 because magnesium usually gives out. So it's already an ion here. Magnesium ion here, that is, when it's in solution, is in form of ions, goes to the negative cathode to pick up electron or gain electron, which is reduction. So magnesium picks up 2 electrons because it has 2 charges to become neutral. That's magnesium solid. Now we can see here that 2 electrons are required to liberate or produce 1 mole of magnesium. We use liberation for gases, sorry. So in this case now, 2 electrons is equivalent to 2 Faradays because 1 mole of electron is equivalent to 1 Faraday. So if we have 2 Faradays here producing 1 mole of magnesium, the question is to calculate the mass of magnesium that will be liberated by 8 Faradays. Now we have 2 Faradays here. We don't need to change it to coulombs because you all know that 1 Faraday is equivalent to 96,500 coulombs. But here we are not using coulombs. We have to deal directly with the question using Faradays directly, and then mass of magnesium. So 2 Faradays produces 1 mole of magnesium. Please take note of this. 1 mole of an element is equivalent or equal to its atomic mass or mass number. So since magnesium is in form of mass and we have 1 mole from this equation, we have to convert this 1 mole of magnesium to its molar mass or molecular mass or mass number or atomic mass. So 1 mole of an element is its atomic mass, and the atomic mass of magnesium has been given as 24. So here we have 2 Faradays producing 24 grams of magnesium. So 8 Faradays will produce what? X gram. Cross multiplying, we have 8 multiplied by 24, all divided by 2. So X is equal to 96 grams. 96 grams of electricity, that's this gram of magnesium is required by 8 Faradays of electricity. Assuming we are asked to calculate the mass of copper deposited by using 2 amperes for 60 minutes. This is a very adequate information to calculate the quantity of electricity and then use it to calculate the mass of copper. Now, with these 2 amperes and 60 minutes that is given, we can work out the quantity of electricity, which is measured in coulombs. And then I here represent the current, while T is time that must be in seconds. So time must always be converted to seconds. So to calculate the quantity of electricity here, we have 2 multiplied by T, which is 60 multiplied by another 60. This is 60 minutes. It should be converted to seconds, and that should give us 7,200 coulombs of electricity. So it means that 7,200 coulombs of electricity will deposit what mass of copper? Now, the first thing to do is to write the half reaction. Now, we are dealing with an element called copper A. So copper, 2 ions, when it's in solution, that is in the electrolyte. If you don't understand the principle of electrolysis, you can check my videos on that. I made the first part of this video is on the explanation of the process of electrolysis itself before you can get the calculation. So copper 2 ion here picks up 2 electrons, which is reduction. That's gaining of electron is reduction to liberate neutral copper element. So here now we can see that 2 Faradays of electricity is required in this equation of reaction to liberate 1 mole of copper. Now, so we have 2 Faradays in the equation liberating 1 mole of copper. Now, we need to convert copper here to mass, and we need to convert these 2 Faradays that we got from 2 electrons, because 1 mole of electron is equivalent to 1 Faraday. And 1 Faraday also is equivalent to 96,500 coulombs. So if we have 2 Faradays, that is 2 multiplied by 96,500 coulombs from these 2 electrons, which is equivalent to 2 Faraday and then 2 times 96,500 to liberate 1 mole of copper, or to produce 1 mole of copper. Now in this case now, 1 mole of copper in mass, it is known that 1 mole of an element or any element is its atomic mass. So what is the atomic mass or mass number of copper? The atomic mass of copper is 64. So 1 mole of copper is equivalent to 64 grams. 2 moles of copper will be 2 multiplied by 64. But in this half reaction, we only have 1 mole of copper. So copper 2 times 96,500 is equivalent to, we produce 64 grams of copper. So this 7,200 that we got in the question will produce what mass? That is S gram of copper. You can see that everything is arranged together. We have quantity of electricity on one side, the mass on one side, then we cross multiply, X multiplied by 2 multiplied by 96,500 equals to 7,200 multiplied by 64. Dividing both sides by 2 times 96,500 coulombs. We have our answer as We have our answer as 2.387 grams. So 2.387 grams will be deposited by 7,200 coulombs of electricity from the given a question like this. What time is taken for 6 grams of gold to be deposited if a current of 5 ampere is passed through a solution of gold trioxonitrate 5? Now we can see here gold, the atomic mass of gold is 197 and 1 Faraday is equal to 96,500 coulombs. We had to calculate the time and the mass was given, but using this formula, Q equals to IT, which represents current multiplied by time, where time must be in seconds. But if the time is in the options now, for instance, now in this option, time is given as minutes, then we leave our answer as minutes. Now here, quantity of electricity is equal to current multiplied by time. Current was given to us, time was not given, and the quantity, which is Q, was not given as well, because we would have gotten it if we multiply current with time, but we were asked to calculate time, whereas quantity was not given. So how can we get the quantity of electricity? This 6 grams can lead us to getting the quantity of electricity. Now, what is the element involved in this question? Gold. Now, let's write the half reaction. Gold, which is aurum, carries +1 as its charge. Because it's electropositive, it goes to the negative cathode to pick up electrons. So that is reduction taking place at the cathode, while oxidation takes place at the anode. Now, it's going to pick up 1 electron to become a neutral gold, which is solid. So it means that here, it requires 1 mole of electron. And 1 mole of electron is equivalent to 1 Faraday, which is also equivalent to 96,500 coulombs. To liberate or to produce 1 mole of gold, from the equation, 1 electron is required to produce 1 mole of gold. Now, let's write it in full. Since we need Q, we want to calculate Q, and Q must be in coulombs. We need to use this, 96,500, instead of using Faraday, because the question is not talking about Faraday. So we have 96,500 coulombs, because it is 1 electron, is required to liberate 1 mole of gold. But in the question, we have 6 grams of gold. So it means we must convert gold to gram. Now, we don't need this now. This is the first line. We got this first line from the half reaction. That is 1 mole of electron is required to produce 1 mole of gold. 1 mole of an element is equal to the atomic mass or mass number. And the atomic mass of gold here has been given as 197 grams. So it means that 96,500 coulombs produces 197 grams of gold. So 6 grams here of gold will require what quantity of electricity? So here now we have X multiplied by 197 equals to 96,500 multiplied by 6. Dividing both sides by 197. We get 2,939.1 coulombs. So it means that Q here, to produce 6 grams, requires 2,939.1 coulombs. So using Q equals to IT, where Q is 2,939.1 coulombs and our current is 5. What is the time? So from here, we can just get our answer by dividing both sides by 5. T equals to 9.796 minutes, which is roughly 9.8 minutes. Looking at the options here, we have 9.8, which is option B.